So let me summarize what we did last time. We introduced a few formal tools, like what is the Hilbert space we are talking about, the scalar products, Hermitian operators, and with that we were able to prove the first important property, which is the following, that the only reasonable way of defining a probability of finding a certain particle at position x and time t, that must be the square modulus of the wave function. Okay? There's nothing else that satisfies the important property that the integral over all space of this probability is conserved in time. So if you take the derivative with respect to time of this quantity, you get 0. Okay? And we proved this by essentially using the property that the Hamiltonian H, which I remind you is what governs the time evolution of psi in the following way. Okay? So this is the Schrodinger equation, the first order derivative in time with I h bar in front of psi equal to the Hamiltonian operator applied to psi. Where this Hamiltonian operator might even depend on t was not essential in our proof last time. Does not necessarily has the simple form p square over 2m plus a potential. Might be more complicated than that. There might be magnetic fields and all kinds of things. In fact, it was a very general proof in some sense, if you just view it again. And it was based all on the fact that H is Hermitian. Okay? Or in other words, when you have essentially two states, then H can travel back and forth, and this is what you need. In our special case yesterday, there was the same state, but in general, it applies to two states. Okay? Any Hermitian operator has this property, and H in particular is, say, the queen of all Hermitian operators. Okay? So it is not really, strictly speaking, for only this thing. In fact, it's much more general. It holds also for a system with more than one particle. In some sense, you have to generalize, obviously, what you mean by x. It means the position of all particles and so on. But it's much more general than just this simple thing. Okay? So, probability of finding x and t. You know from classical probabilistic theory that if you have a certain probability distribution, you can calculate the average of a certain quantity. Okay? So here you know the probability of finding x, and you can calculate the average x. Okay? How would you do it if not in quantum mechanics, just in any elementary statistic course? You would integrate over x, all points, then you put x, and you put p of x, right? Well, x, y, or z, obviously, any component. Okay? This is the most obvious thing, okay? When you have a probability which is normalized, you multiply by the variable that is the average. If you want to calculate the standard deviation, okay, how it's called, the sigma, then you have to calculate the average of the square minus the square of the average, for instance. Okay, so all moments in principle can be calculated, first, second, and higher moments. But now let us rewrite this. Okay, let me write it for x only. P is psi modulo square. So I can equivalently write this as x psi star x psi x t. Okay? And now we learn our rules. Okay? This is nothing but, let's see if I can convince you, the scalar product between the operator x applied to the state psi, scalar product with psi, right? Because all you have to do is to write an integral where you have here this object, which is here, okay? Remember that x acting on a state simply is a multiplication by x. And on the left, you put the star, psi star, okay? So you see this is nothing but the sandwich, in some sense, of the operator x between the states, there and there, okay? This way of calculating expectation values is very, very general. So I will define, in some sense, the expectation value of any operator O at any time t to be just the sandwich where I apply the operator to the state, and then I take the scalar product still with the same state, where this is the state at time t, okay? So the one that obeys the fundamental dynamical equation of this problem. Yeah? Which one? This one? Last one. This one? This one?
If x was not initial, because x is acting on the gate.
First of all, I'm talking about x, position, x. This example here is for x position, which is Hermitian. Okay?
If the operator was not Hermitian.
Now, this definition here, in principle, holds true for any operator because it's almost a definition at this level.
I'm talking about the connection with the integral form.
Well, you can write in integral form this thing if you want, okay? And if the operator is not Hermitian in principle, well, you have to act on the right, okay? So it's not the same thing as acting on the left. Okay, this is the definition. Which one?
The integral form with x. X should act on psi of x in the integral form. If x is not Hermitian, I think.
But x is Hermitian, okay?
Yes. Okay, I'm talking about.
You don't want this written in this way. You want to write it this way. It's the same. I mean, it's the same. It's the same. Okay.
X is Hermitian. Okay.
What I mean is that you always have to define this way. The operator acts on the right, okay? With this definition, it's true for any operator. If it is Hermitian, then you can also act on the left. If it is not, no. But I don't write here or there. There, okay? Fixed. All right? In most cases, we'll meet Hermitian operators, and therefore, the thing is unambiguous, okay? But in case, just put it there, to the right. Okay. Now, you can prove for me that whenever a certain operator is Hermitian, okay? So, to write it explicitly in integral form, this would be psi star, the operator acting on the state x. Okay, whatever it is, it has to act on the right. Notice this might be involve derivatives and things. The derivatives act on the right, okay, not on the left. Okay, one important property. And by the way, suppose that I ask you to calculate the expectation value of momentum. So this is the momentum operator. Say the momentum in the x direction, for instance. Okay? Now, all you have to do to follow this procedure is to put here the momentum operator, which is minus I h bar, the derivative with respect to x. Now, this derivative acts on the right. All right? Now, let us show together that whenever the operator O is Hermitian, so let me write here. If O is Hermitian, then the expectation value of O, defined in this way, is real. It's a real quantity. If it is not Hermitian, it might be complex. But if it is Hermitian, it's real. The proof of this is very simple, but let's do it. So I encourage you to follow the very simple steps here. You remember our definition of scalar product, and you have to be careful that if you take the star of a scalar product, as we have defined, remember that there was a star in the integral for the state staying on the left. So if you take the star, it's easy to prove that it's the same thing as reversing the two things, okay? Just from the very definition, okay? So this is an important property of scalar products. The star exchanges the two things. Okay, so let's take the star of O, of this object. So O star. According to our definition, this is psi. Let me omit the t, okay? It is assumed that it is a state at a certain time t. Doesn't matter, okay? Psi, O acting on psi star. Okay? But according to this property of the scalar product, I can bring this on the left. Okay? So this is exactly identical to O psi psi. All right? Now, O, however, is Hermitian, and therefore it can travel. It can go to the right, no price. Okay? So I can write this as psi O psi. And now, you look at the definition again, this is just the average of the operator. Okay? So you prove that the average of the operator is equal to its star, and therefore is real. You see, many of these proofs in quantum mechanics are very simple. They take just a few lines of patient algebra, nothing really astonishing. So please be patient and work with the rules, and you will get things right. This implies, for instance, that the average of the momentum is real, although the momentum has an I there, okay? As we said last time, this is just because there is an I. So, because it is strongly connected to the fact that the momentum is Hermitian. So the Hermitianity and the fact that the value is real are both due to the I, because essentially the I allows the change of sign needed in the integration by parts. If you go back to the proof that P was Hermitian, you will notice that the I was crucial in the proof because of the change of sign that is typical of integration by parts. Okay? One thing, you shouldn't think that P is a fundamental object of quantum mechanics. I mean, P is important, is the probability of finding a particle somewhere, but the fundamental object is psi, this. You see, I didn't write an equation for P. We will do it in a second, but it's not a closed equation. It involves P and other quantities, while the equation for psi is perfectly closed, I mean, given the Hamiltonian, obviously, okay? So psi is fundamental, not P. And to notice this, you see that in general, to calculate an expectation value, you need not P, you need the operator acting on psi and then taking the integral with psi star. For instance, the expectation value of P involves the integral of psi star times the derivative of psi, which is not p, okay? So p is psi star psi, but sometimes you have to take a derivative of a certain piece and not psi star, and therefore this is not given by p. If you know p, it's not enough, okay? It's not enough to know the following evolution to calculate certain expectation values and so on, okay? So in some sense, this puts p in backstage, okay? P is not as important as psi. Okay. One final word about notation. Sometimes you use what is called the Dirac notation. The Dirac notation is a kind of useful object. For instance, when you write this object in Dirac notation, you put an extra bar here, okay? So in some sense, the operator O is really sandwiched between the state and another object that Dirac called bra, okay? This is called the cat, and this is just the bra. The bra is what appears in the scalar product with the star, okay? So in an object like this is the integral of psi 2 star psi 1, okay? So you see the bra appears with the star, the cat not, okay? And this is also nice because in this way you really see that you have a bracket type of thing. So it's a kind of terminology that reminds you that you are sandwiching the operator between the cat, the state, and this corresponding bra. Okay? Just a notation, nothing really deeper than this, at least as far as I know. Okay. A couple of exercises, actually one, but I encourage you to do it. I will guide you through it. Okay? Most of it we will do it, but I think you should do it yourself. And the exercise is the following. It has to do with Eisenberg uncertainty principle, which we already saw in some sense behind our Gaussian wave packet story. Okay? You remember that the uncertainty, the width of the Gaussian in K space and in X space were quite inverse to one another, and the product of the two was exactly 1/2, if you remember. There was an H bar missing, obviously, because I was considering K, not P, but apart from that, this 1/2 is probably what you should remember. Now, let us define a few things. If you have a certain wave function, let me sketch it, okay? Wave functions are usually complex, so it's difficult to even sketch them because you should sketch a real part and the imaginary part. Let me just suppose that you have something, okay, some psi. Now, you can calculate the average of x, okay? Say, for instance, the average of x comes to be something close to here, okay? You have to multiply x times this modulo square of this, and then you can also define what is the spread, the width, okay? How? Well, as we said, in the very natural probabilistic way. So x square average, x is an operator, so x square average is perfectly well defined. How would you define it? Simply integral in dx, well, let's define as psi x squared psi. If we put the Dirac notation, let's put an extra bar there, okay? So that is the average of x squared. Now, x squared minus the average of x squared is what I will call delta x squared, okay? For me, is the second moment of this thing. So it is something of the order of how width is the wave function in position space, okay? And this is simply, well, whatever you have. Here, this one minus this squared, okay? So psi x square psi minus psi x psi square. Okay? It's a very sharply defined object. The same thing you can do for P. You can define the average of P, as we have seen a while ago, and subtract this from the average of P square. Okay? This will be the uncertainty in P. Okay? Tell you how well P is defined in a sharp way. Okay? Which is related to, obviously, the Fourier transform of this thing. Okay? The Fourier transform tells you the P content. And the more P is sharply defined, the more the Fourier transform is peaked. Okay? But you realize that the very peaked P means that the Fourier transform has a single momentum, means that in X space oscillates like a plane wave. Okay? So it's very delocalized in space. Okay? So in some sense, sharp in P, it means extremely delocalized in space, plane wave. And vice versa, extremely sharp in X, it means that when you calculate the Fourier transform is flat in P. Okay? So very broad in P. You remember that the Fourier transform of a delta function doesn't depend on P. Is this clear to everybody? No, again, okay. The two quantities, okay, psi x and say phi of P and G of P, we called G of P last time, okay, the weight, are, let's work in 1D, not to be, they are related by this object. In fact, we call G of K, okay? This means psi is the Fourier transform of G of K. Vice versa, there is an inverse formula. G of K is the Fourier transform, inverse Fourier transform of psi of x, okay? With exactly opposite sign here and integral in dx, okay? Let's write it, something like this. Okay, these are formulas that are one opposite of the other, one inverse of the other. Okay, sometimes people call this phi of P, is the wave function in momentum space, okay, rather than G of K. Okay, now, what I was simply saying is, if G is a single peak in momentum K, say at K0, some delta function there, then when you do this integral, you just get a single K0, which means that psi of K is e to the I K0 x, a plane wave, okay? Oscillates forever, very delocalized, okay? On the contrary, if psi of x is a delta function, okay, so centered into some point, say 0, for instance, then when you do this integral, the essentially x equals 0 remains only, and what you get is a quantity that is constant, 1. 1 over 2 pi, whatever, okay? Independent of k, okay? Which means that G of K is totally flat in K. So you see the duality, okay? Something sharp becomes something broad in the complementary space and so on. Now, we want to know, in general, not for these very limiting cases, like a single delta function, a plane wave, a flat thing. We want to know, in general, how the width of the distribution in X and in P, okay, so of the distribution or of its Fourier transform distribution, are related, if there is a bound between them. And we want to prove the very famous bound that the product of the two uncertainty should be always greater than h bar over 2. Okay? This is called the Eisenberg uncertainty principle. In other words, in no state in nature, you can prepare the state in such a way that both x and the momentum are infinitely sharply defined. Okay? If you decide that you prepare a state that is very well localized in x, you have to pay in p. And vice versa, if you prepare a state that is very well localized in momentum, then you pay in x. It's broader in x. Okay? Because of this fundamental bound. Okay? Is this clear? We want to prove this in general. Now, if you do the exercise that is indicated as exercise 1.5 in the notes that you got, right? You got the notes. You will be guided through the obtaining this equation. Let me just provide to you a couple of hints. The crucial thing is the following. We'll later on prove similar bounds for any two operators that do not commute in a slightly more general way. But I think that this is somehow more intuitive, okay? Although, strictly speaking, still related to the fact that x and p do not commute, okay? If you calculate the commutator of x and p, you probably know the result. You have seen it before. It is I h bar, okay? In other words, it makes a difference if you first apply the momentum and then multiply by x, or on a state, or you first multiply by x and then apply the momentum. Okay? The difference between these two ways of applying the same two operators, it is related to the fact that in the second case, p, which is a momentum, so it's a derivative, has to act, as you know for any derivative, on two things, not one. In the first case, it acts on one, and then x multiply. In the second, it can act on psi, like here, but it can also act on x, leaving psi untouched. Okay? And it's exactly this first piece that survives when you take the difference. Okay? Because when you take the difference, the second term, so p acting on psi, cancels exactly with that. But the first survives. And the first is exactly, for any state psi, giving you minus I h bar. The derivative acting on x is just 1. Okay? So just I h bar. Any psi. Okay? No, it doesn't matter what is the psi. Okay? So this is the fundamental commutator between these two operators, x and p. By the way, they are called canonically conjugate because of that. And the way to prove this Eisenberg uncertainty is the following. Let us construct the following object. It looks a bit strange. So let us calculate the integral of the modulus square of x minus the average of x psi. By the way, you immediately see that you can rewrite this as x minus the average of x square. Let us prove this first. Which immediately show that this quantity, by the way, has to be, cannot be negative. If you write it this way, you see it immediately. Why these two quantities are the same? Because if you expand the square, you will see that there is x square plus the average of x squared, and then you have two terms, okay, which are exactly identical, that are minus twice the average of x, and x alone survives in here, which is again average of x. Okay? So this is exactly equal to this. So it cancels this plus and makes it a minus, as it should. Is this simple algebra clear to everybody? Okay? So writing this way or this way is exactly the same thing. But this shows that it's positive. Okay? So you see, I'm taking this piece here and putting there. Then I have the similar object here, which is the average of P minus average of P squared. And let me put it here, P minus average of P, okay? Applied to psi. Let me put some constant in front, and then I take the modulus square, okay? And for a reason that will be clear in a while, it's nice that this quantity is real, and there is an extra I there. It looks bizarre, I understand, when you see it the first time. But think of this. The modulus square of this, okay, is essentially what appears there. If you write this explicitly, you will see that you get the modulus square of this. Okay? The modulus square of this is what appears there. Then this quantity also has a mixed term. Okay? And the mixed term is what makes the exercise interesting. And you will see the role played by alpha and by I in this mixed term. And by the commutator, by the way. Okay? Now, this quantity here, that is called d of alpha. Okay? It depends on the real quantity alpha. Alpha real. Okay? And is an integral of a modulo square of a quantity. Therefore, you can immediately conclude that it must be positive. Okay? Now, I want to argue with you and guide you through simply to show that the dependence of this d on alpha is very simple. It's quadratic in alpha. You see, there are obvious terms that do not depend on alpha. This is a constant. A term that depends on alpha square, this modulo square. And then there is a linear term coming from the mixed term. Okay? So please prove for me, or for you, whatever, okay, that this quantity is equal to delta x square, is obviously coming from here, plus alpha square delta p square, obviously coming from the square of that, and this is the only tricky part of the exercise, try to do it, minus h bar alpha. The h bar comes exactly from this commutator here, okay? The alpha linear comes because it's a mixed term that you are considering, okay? And due to the I, you have a minus here, okay? So, after having realized this, and from the fact that this is greater or equal to 0 by construction, then you realize that this is a parabola. If you draw it as a function of alpha, it must be a parabola that is never negative. It means that it can be something like this, or at most something like this. Okay? But not something like this. Now, what is the property of parabolas that are not of this type and are of these two types? You know how to distinguish a parabola of this from the coefficients, a, b, and c of the parabola. Right? Remember, if I have a x squared plus bx plus c, How do I know if there are two real roots or not? Huh? Discriminant, okay? So you calculate b squared minus 4ac. If it is positive, then there are two square roots, and you are in this case. If it is negative, you are in this case. If it is 0, you are in this case. So discriminant less or equal to 0, it is this case. Okay? So now notice this is your variable, alpha. So call this x squared. Rearrange the things. This is the x squared, and this is the a. This is the x, and this is the b. And this is the c. Okay? And calculate the discriminant, b squared minus 4ac. You see that b squared is h bar squared minus 4a is delta p squared, and c is delta x squared. And you want this to be that, okay? So immediately bring this on the other side, and you see that you have h squared divided by 4. Take the square root, and you conclude that this is true, okay? So you see how to, I mean, this is the crucial point. If you prove this, then that equation comes simply from the fact that this should be positive by simple, I mean, algebra of parabolas. Okay? Please fill the details. Not many, but important. Questions until now? Okay. Maybe, if you want to be even more sophisticated, you could try to prove for you what is the minimum, the bound. In other words, what must be the state when you have an equal sign there? A hint to this should be the fact that when we work with the Gaussian wave packets, we got just equal. So I anticipate for you that the solution is Gaussian wave packets realize the minimum uncertainty that Eisenberg provides. Okay? But you could try to prove this from here. Okay? See if you can work it out. Okay. Yeah.
Which quantity is that d of alpha?
Which quantity?
Okay, physically, which quantity is it? What would we compare it to? If we
That is exactly the weakness of this exercise. It looks like it's falling from the sky because I gave you a quantity, which, I mean, it's reasonable. There is a modulo square, and so it's a reasonable thing, positive certainly, and it mixes apples and potatoes in some sense, okay, because there are x and p. However, it mixes it in just the right way. For instance, this apple square are exactly the uncertainty in x. This potato squared are exactly the delta p square. And there is a square and there is a linear term. And obviously, it takes a little bit to construct it. So suppose that I now tell it to you and you forget it and you try to reconstruct the ingredients. It will take a little bit for you to exactly put together the two pieces. But in the end, the following thing is quite elegant, right? I mean, it is a very simple expression in alpha, which allows you to conclude, I mean, almost no effort, that this bound is verified. Okay, so don't ask what is the physics of it. It's a mathematical invention, which shows, however, the thing that you want to show. Okay? If I ask you to prove that for any state this bound is satisfied, and you start working on it, you don't know where to start from. But how can I prove it for any psi? It's an infinite possible choice of functions, and I should. Well, that is a route to the proof. Okay. So as it happens in mathematics, sometimes you construct objects that are unclear at the beginning, but they have all the ingredients to show you something that has a deep physical meaning. Okay? I hope I have answered the question that was, I repeat it again, where does this d of alpha comes from? From nowhere. I mean, from the mind of some brilliant guy that first thought of obtaining this bound from simply putting the ingredients in the equation there. Okay, let us go back to P for a second, if there are no more questions. And let us try to answer the following thing. Yeah. Left to
left to the right. And physically, how can we interpret this?
The question is, Hermitian operator can go from right to left in the scalar product where they enter. And he wants to know physically how to understand this. Very difficult question, confining towards philosophy. I mean, physically, what should I say? I do not have a very sharp answer for that, okay? You have a physical intuition of why? Okay, we can discuss that, okay? One can try to find many answers, but no obvious, direct and sharp answer, I mean, that I can think of in 1 second, okay? So maybe this is something to discuss somewhere at lunch or something, but not really. I mean, the fact that the expectation values of Hermitian operators are real is already a big physical hint towards the fact that, I mean, what you measure is real quantities, okay, physical observables. And this is, I think, why all important operators, most of the measurable things are Hermitian operators. There are measurable quantities like Berry phases that are not standard Hermitian operators, by the way. They also have a physical meaning, a physical influence, but I mean, all the other operators that I can think of, momenta, angular momenta, Hamiltonians, potential energy, and so on, all associated to obvious things that you can measure, and they have real values, and they are associated to Hermitian operators. But I don't know if this is an answer that satisfies you, okay? This is the answer I can think of in 1 or 2 minutes, and therefore that's enough for the time being, okay? Now, suppose that I, rather than putting this integral here, I try to calculate directly the derivative of P, okay? So let me ask you, what is the derivative with respect to time of P, x, and t? I write now partial derivative as opposed to the total derivative because now I have x and t, and so to distinguish that I have just the derivative only on x, on t, I have P of t. Well, this is simple, right? Because this is psi star psi, so this is the derivative of psi star psi. Let me omit the variables. And you know both, right? Because you know that, well, it's written here. I h bar, the derivative of psi, is equal to h psi. And obviously, if you take the star of everything, minus I h bar, the derivative of psi star is h psi star. Okay? Therefore, this object put the IH bar to the right is equal to, if I take the derivative of the second, is 1 over IH bar times H psi times psi star. Okay? This is from the derivative there. And the other is, you see, I have minus 1 over IH bar H psi star times psi. Okay? This is the direct calculation of the two things. By the way, obviously, if you reintroduce the integral over x here, then you immediately see that what you have here is just psi h psi minus h psi psi, which is 0 because h is Hermitian. The proof that we gave last time. Okay? But now we do not have the integral, and therefore this is not a scalar product. It's just psi star times h psi minus. Okay? Now, let us assume now for this lecture, I will assume really the form that we gave, p squared over 2m plus v. You see that the term in v, for instance, present there, it gives you psi star v psi minus, okay, let me put this in front, okay, and leaves just a minus sign, minus v psi star psi. But v is a real potential, and therefore you can take out this from the star, put it there, and you see that it's exactly the same. So the potential drops out completely. Okay? So all it remains there is just p squared over 2m. Okay? Or, said it different, the Laplacian. Okay? So you can express this as follows. You can rewrite this as 1 over I h bar psi star. P squared is minus h bar squared, the Laplacian, okay, over 2m. So let me write the Laplacian here, but the minus h bar squared and the 2m in front. Okay? Similarly here, minus Laplacian of psi star psi. Was the calculation clear to everybody? Everybody, please. A nod? Yes? Okay. Good. Good. So the h bar really simplifies a little bit. And if you want, just put this I on top with a change of sign. So let me rewrite this in a cleaner way. This is equal to I h bar divided by twice the mass. Okay? Good. Now, there's still some manipulations that I can do here. I want you to remember the following thing. Suppose that I have the divergence of something. You remember what the divergence of a vector is, by the way? The divergence of some vector. The notation here should simplify the thing. Derivative with respect to x of the x component plus derivative with respect to y of the y component plus derivative with respect to z of the z component. Okay? Well, this is obviously a vector field, okay? So it should depend on the position. Otherwise, there is no meaning in calculating the gradient of the components, okay? Is this remembered by everybody? This is also sometimes indicated by divergence of J. Okay? Good. Now, suppose that instead of having this vector here, I put there psi star the gradient of psi. After all, this is a three-component vector because the gradient has component x, y, and z. Okay? So it is a legitimate vector field, right? Like J. So let us try to calculate the divergence of this. Now, you notice that there is the derivative that I have to take, and I can take it in two possible ways, either here or here. Okay? So it is not difficult to prove that this is exactly equal to, let's see, it has to be, in the end, this is a vector, scalar product with another vector, it has to be a scalar. How can you make a scalar by these ingredients? There are two possible things. One is you take the gradient of psi star and you dot product with the gradient of psi. And this is exactly the term that originates if you take the derivatives on the first piece only. Okay? Plus psi star, the Laplacian of psi, which is the term that originates when you take the derivatives there. All right? So try to please do it with all the indices that you need to be perfectly happy and satisfied with this vector analysis formula, which is that the divergence of something that contains a gradient is gradient plus Laplacian. Okay? They're both scalar quantities now, you see, because here there is a scalar product and here there is just a Laplacian. All right? Okay. Now, if you realize this, then it's simple to show that that the quantity that you have here is nothing but the divergence. You can write it as minus the divergence of a precise object, J of x, where this J is the following. It is equal to minus I h bar over, let me write it and then we comment on why this is so. Psi star grad psi minus grad psi star psi. Okay? Everything here depends on x and t, obviously. Okay? I'm just omitting the variables for the psi. Okay? So let us form this J to be, apart from this constant, psi star grad psi minus grad psi star psi. Okay? Notice that this is not zero because psi is in general a complex thing. Now, when you take the divergence of this object, so you apply exactly this formula, because you see you have psi star grad psi, for instance, here, what you have is that the first piece, which is this, exactly cancels. Okay? The first piece, when you take the divergence, taking the derivative there, you get grad psi star dot grad psi. When you take the other piece here, you get exactly the same piece, but with a minus. On the contrary, the Laplacian term, so you get the Laplacian here, minus you get the Laplacian there, do not cancel and reproduce exactly what you want, which is the formula in the up line. Okay? So hopefully, with a little exercise, which involves using this vector analysis formula and introducing this object J of x, you can prove that the derivative of P with respect to t is minus the divergence of J. And this now is very physical. I'm talking now in particular to you. Because if you remember, in electromagnetism, when you have charges and currents, charges obviously are conserved. So if they come out of a volume, there is a current exiting or entering, okay? So the integral of a charge in a certain region changes because of a flux of current exiting or entering, okay? And at the basis of this charge conservation, there is an equation that you can write for the charge density and the current density, which is exactly of this form. The derivative with respect to time of the charge density is equal to minus the divergence of the current density. Okay? Now, here there is no electric charge E. It's only density, not charge density, but it is formally exactly the same thing. The derivative of the charge or the number density of probability is just minus the divergence of the current density. So this is a current density or a current probability density. Okay? So you see why P is not fundamental in some sense. P alone, if you take the derivative of it, requires also another quantity that is the density, the current density. Okay? And vice versa, I mean, the current alone is not enough. You need P. And if you start taking derivatives, in principle, they do not end. The only thing that has a very nice equation that does not involve anything else apart from the obvious operator, the Hamiltonian, is psi. So this is called the continuity equation, and you again have seen it in classical electromagnetism. It simply expresses microscopically at the level of densities the conservation of charge, in this case the conservation of probability. Okay. Things that enter or exit change the total number of things in a certain volume. Okay? Is this clear? Okay. In 1D, this is particularly simple because the divergence of J is simply the derivative of J. There is only a single piece. Okay? Okay. Now, let us continue a little bit with the case where H, again, doesn't depend on T. Let's see if we can say a little bit more about psi of x and t when the Hamiltonian doesn't depend on t. Let me erase here a few things. Formally, what we said is the following. There is an operator U, the evolution operator, which we explicitly wrote as the exponential of the Hamiltonian with this factor minus I t over h bar, such that if I know the psi at a certain time 0, by applying it, okay, to the wave function at initial time, I obtain magically the wave function at time t. Although we stress the fact that this operator is very complicated. Formally simple to write infinite series of powers of h in the exponential type of expansion, but it involves a very complex object because, I mean, this involves powers of the Hamiltonian of all types. Nevertheless, it is intriguing. I mean, let's ask the following problem. Can we find solutions? Okay, you see, at the beginning, the thing is just t psi of x and 0, and then becomes by this application some psi of x and t. But can we find special solutions which are of this form? Some function of t times some function of x. Okay? This would be very nice. Okay? At least the complexity of the wave function, it's now a little bit reduced. It's a product of two functions. Okay? Let's see if we can find this. Well, it is not difficult to find the solution for this. And you could find that the only possibility is that, let me write first the solution. Or rather, let's derive it. Let's derive it. Okay, so suppose that I have a solution of this form. Let's plug it into the Schrodinger equation. So I have that I, h bar, the derivative with respect to time, of f times phi is equal to the Hamiltonian, which doesn't depend on time, times f phi. Okay? Notice, for every time, this is just a number, a complex number, okay? The Hamiltonian has operators like Laplacian and things, and you can bring this out. So you can also write this as, by linearity, f of t Hamiltonian applied to phi of x. Okay? Okay, on the same, at the same time, here the derivative acts only on f, not on phi. So I can write this as I h bar, the derivative with respect to time of f of t, times phi of x is equal to f of t times h phi of x. So you see that now, in order for t and x to be really completely detached, what you need is that this equals this, and in some sense, this is related to some constant times that. Okay, can you see the way t and x really? Okay, so let's see. You could proceed a little bit formally. For instance, suppose that f of t, it's different from 0, and also phi of x is different from 0, then you can divide everything by f, and you would obtain something like this, divided by f, equal to, and divide everything by phi. It's just to show you. I mean, you do not possibly have to really do this, but just to show you. If they are different from 0, certainly you can do that. Now, how is it possible that a quantity here that depends only on time is equal to a quantity that depends only on x? Just constant are the ring of conjunction between these two possibilities. Okay? So let us call this constant E. Okay? So you realize that the only possibility for having factorized solution of this type is that h phi of x is equal to E phi of x. And at the same time, if this is IH bar derivative equal to E psi, f of t equal to e to the minus I E t over h bar. The solution of this is very, very simple. It's just an exponential. Okay? So this is the only plausible possibility for factorized solution. Now, is this one solution? Two? Infinite in general. Okay? First of all, realize that this is an eigenvalue problem. In other words, the phi here is the eigenvector. and the E is the eigenvalue. Now, H is an admission operator. There is a theorem, which I'm not going to prove, but we will essentially realize that this is the case in all the cases we will study. And there is a theorem that says that any admission operator admits an infinite set of eigenvectors which forms a basis of the Hilbert space. In other words, you can expand any state. A basis of a linear space, you know what it is, right? Is a set of states over which you can expand and express any other state. Like in Cartesian space, the three vectors of the axis are a basis set, right? Okay. The eigenvectors, you can write by classifying with an index n an integer or collection of integers or whatever. It's not unique, the thing, okay? Can be a simple integer or a more complicated set of labels. But the important thing is that there is an infinite set of phi n, okay, which are eigenvectors of the Hamiltonian with corresponding eigenvalues En, again an infinite set of them, and that this is a very nice basis for the Hilbert space H. Okay? Now, yeah.
Here, when you say that this division here holds only if f and phi are different from 0.
Yeah, I mean, this is different from 0. So in some sense, it's what, in principle, I should be a bit careful to is the phi. Phi sometimes at certain positions might be 0 because there are zeros, not the ground state usually, but the excited states. There could be certain positions where this is.
Maybe we would have made that assumption from the very start, because if any one of them is 0, then phi is 0, then psi is 0, it's 0.
Right.
So maybe
There is nothing wrong with the psi being 0 in a certain point or in more than one point. Nothing wrong with that, okay? It's simply that at those points, you shouldn't do the step that I did here just to show you the idea. But even if it is not at every point, as long as you can do it at, I mean, a sufficient number of points, you realize that here you have a quantity of x, and here you have a quantity of t. The only possibility is that these are constants, okay? It's true, not all x possibly are such that phi of x is different from 0. But, I mean, the vast majority of them are, and in any case, you see here that this doesn't depend on x. So I can change x. If phi of x is 0, then I change it a little bit. Close, it will not be 0. If it is 0 everywhere, it's not a wave function, okay? Obviously. Okay, in any case, you can prove directly, if you want, that if I have functions that are eigenfunctions of the Hamiltonian multiplied by the eigenvalue times t and times whatever, okay? These are solutions, okay? You can prove that these are solutions of the Schrodinger equation. They are not generic solutions. They are very specific solutions, okay? They are called energy eigenstates, okay? These are energy eigenstate solutions. Notice, they are so special that if you calculate, for instance, the p of x and t, calculate p of x and t for those eigenvectors of the Hamiltonian. Well, you have the modulo square of this, so the modulo square of e to the minus ent over h bar phi n of x. And you see that the phase, this energy phase, cancels exactly, and you have phi n x modulo square. So this doesn't depend on t. That's the reason why they are also called stationary states. In some sense, their probability distributions do not evolve at all. Okay? They're just constant in time and equal to the modulo square of the eigenstate square. Okay? Consequence of this is that the derivative with respect to time should also be 0, or if you want, that the divergence of the j for them, so the Jn, should be 0. So, for instance, in one dimension, you can immediately conclude that the current should have 0 divergence, so dx should be 0. The current should be constant. Okay? So the stationary states have also a constant in space current. Okay? We will explore this later on when we will study some one-dimensional cases. It's important that you just realize that they are they have particular properties. Now, let us see. Suppose that I tell you, okay, the state at time 0 is just a stationary state of the Hamiltonian, so it's phi n of x. What is the time evolution? Let me ask the question without this interlude that we have done. What is the time evolution? Well, according to our rule here, I should apply in front of this the e to the minus I h t. Okay? So I apply this operator to the state at time 0, which is the eigenstate of the Hamiltonian phi n. Well, but if h phi n is equal to the energy times phi n, any power of h is also equal to any power of the energy. For instance, let me just be specific. H squared phi n is equal to En squared phi n. Very simple to prove. Okay? H cubed is equal to En cubed. Okay? And so on. Therefore, this operator here that we discussed before is very complicated in general. It's very, very simple when acting on the energy eigenstates. Okay? And only then is simple. So on this thing, I can do the calculation in one line and conclude that this is equal to e to the minus En t over h bar phi n of x. Okay? So the state at time t is nothing but a pure phase times the state at time 0. Okay? Which is exactly the result we have also derived by that interlude. Okay? Is this clear?
Sir,
Yeah.
could you give us a physical problem where we cannot write the wave function as the product of the space part?
You will find an infinite number of applications where this is not true. In fact, suppose that the initial state is a certain, okay, let's do the following. Suppose that the initial state is equal to alpha, a certain eigenvalue n, plus beta, a certain different eigenvalue m. This is possible. I mean, after all, this is a basis of the state, of the Hilbert space, and my function might be just a superposition of two of them with two coefficients, okay, such that obviously the modulo square of this integrated is 1. Okay? Is this clear?
Yeah, okay. Well, we start by saying if we can write the wave function as a product of space part and time part.
Yeah, but not for all wave functions,
Yeah,
for spatial wave functions. Okay?
Okay. Can you give us where, yeah,
This one. Follow for 1 second and you will have the example. Now, calculate the evolution. So apply e to the minus ht over h bar to this function. So to alpha phi n x plus beta phi m x. Okay? Just do it. For the first piece, the application of the operator to phi n brings you alpha e to the minus I e n t over h bar times phi n of x. For the second piece, you get plus beta e to the minus e m, and this is different, t over h bar times phi m. Now, you see that this is not a product of t times phi. It's sum of products. Okay? This is different from this. You see the difference, right? Looks similar, but it's not. It's sum of products, not just a product.
yeah, but I have, okay, I have some doubt here.
Yes.
My doubt is, we don't know whether phi n and phi m are eigenfunctions of the Hamiltonian operator, because we say phi n is the eigenvalue of the Hamiltonian if we start with the, like, if we can write the wave function or the product of space and then we can
Wait. I think I have made a great confusion in your mind. It's my fault. It's my fault, okay? By stating he's asking essentially, I don't know exactly what, but something that denotes the fact that I wasn't clear at all, okay? I wasn't clear at all, at least with some of you. With this idea, let us look for solutions that are a product of t times a product of x. I just confused you, okay? At least some of you. This is evident from his question, okay? So forget about all I said in that central region if it is confusing. Just forget it, okay? And use a more traditional approach that says, so I erase the incriminated portion of the explanation. So the standard procedure is the following. Well, any Hamiltonian H being an Hermitian operator, one can prove, okay, with mathematical technique, no, not important here, that it has associated to it a set of infinite states, which for practicality I just denote with an index n, but you shouldn't think that this is a single integer necessarily. It might be 3 integers, for instance, like in the hydrogen atom, or might be a more complicated object, okay, set of labels with continuous ranges and so on. But it doesn't matter. It's an infinite set of states that are normalizable, that are orthogonal to each other, that constitute a basis of the Hilbert space over which you can expand any possible state, such that the following is realized, okay? In other words, this basis state is a basis of eigenvectors of the Hamiltonian with corresponding eigenvalues En. This is called the spectrum of the Hamiltonian. Again, is an infinite number of values, which could be point-like, a continuum, both, whatever, okay? Very, very different depending on the physical problem you have, okay? This is something that you can prove in general. At this point, it's pretty obvious that if you start as an initial value state from any of these individual eigenstate, then the time evolution is simple. It's simply a phase factor times the same thing, okay? Which is factorized in the way I was alluding at. On the contrary, if you mix even 2 of them, so for one, it is just a factorized thing. But if you mix even 2 different ones, the factorization breaks down immediately, okay? Because the result of the evolution is a certain phase factor with energy En for the first, plus another phase factor with energy Em different from n for the second, okay? And from here, you can conclude that the general problem is the following. Psi of x and 0, being a state in the Hilbert space, can be certainly expanded, okay, as a certain sum of coefficients, let me call Cn, times phi n of x. This follows from the fact that this is a basis, okay? This is a basis of the Hilbert space. Okay? So any state can be expanded. And in fact, you can even calculate what the Cn are. Okay? How can you calculate the coefficients?
Because since the bases are auto-normalized, then we can multiply from the right by
Exactly. These are normalized already, okay? So if you multiply, it's best to have a notation like this. So psi is equal to sum over n, Cn phi n. You multiply to the, for instance, to the left by some phi m, for instance, okay? Then you have here phi m. And the scalar product of two vectors, okay, is a delta of Kronecker. So this is just delta n m. Is 1 if they are the same, 0 if otherwise, okay? So the delta with the sum simply gives you Cm. Okay, so any coefficient appearing here can be actually calculated by performing an integral, okay? Calculating the integral of this with the appropriate phi m. All right? Okay. So this is, generally speaking, the most general initial state. Now you can calculate again the action of this operator on this general initial state. And now you have to be ready, okay, to have a different phase factor for any of the Hamiltonian. So I have e to the minus I h t over h bar applied to sum over n Cn phi n of x, okay? This is just sum over n Cn by linearity. This one applied to this gives me e to the minus I e n t over h bar phi n of x. Okay? So is it clear? This is the state at time t if the state at time 0 was that. As you see, it looks like a very simple thing to do because you just have to add an extra phase factor e to the minus I e n t over h bar to each of the coefficients. Okay? Looks like a very innocent thing. Okay? But obviously it requires a lot of work. It requires in particular that you know exactly all the eigenstates of the Hamiltonian with all eigenvalues, okay? That you expand your initial state on that basis, that you calculate the coefficients, and then at the end everything is simple, okay? But this large amount of things are pretty complicated. In some sense, of the same level of complication of calculating the exponential of this operator, which I told you was not simple at all. But at least is a different way of approaching the problem. So once you, by any chance, know how to solve this problem, exactly, approximately, or whatever, you do have a way to calculate the dynamics, okay, the Schrodinger dynamics, which is in some sense easier because you have already worked hard to find this part. This is also called Schrodinger equation, but it's called time-independent. Time-independent Schrodinger equation. The previous one, the one with the derivative with respect to time, is the time-dependent Schrodinger equation. And also works for Hamiltonian that depends on t. Here, on the contrary, it's meaningless to have a t in the Hamiltonian, okay? The Hamiltonian must be time independent, and you calculate just the eigenvalues and eigenvector of that. So it's an eigenvalue problem that you have to solve. Simpler, okay? Because there is no derivative over time. But obviously the derivatives that appear in the Hamiltonian, Laplacian, and whatever are still there, okay? So this is not an infinitely simple problem. It's still a differential problem. Okay? And sorry for making that interlude, because I realized that it confused a little bit things. It was just a way of justifying a little bit why I want to construct those objects in the first place. Okay? If I try to see how to obtain something factorized, I realize that the only possible ways is by eigenvectors of the Hamiltonian. But forget about it. Let me state that the eigenvectors are this, and with this, the result is trivial. Okay, here I have a discussion in the notes about free particles and normalization. If you remember, we said the following things. Oh, no. There is a problem that we can do immediately of this type. And then I finish. The problem is the following. Suppose that your Hamiltonian is just free particle. No potential. Okay? So a free particle without any potential. Can we solve this problem? In other words, we have to find functions phi such that minus h squared, the Laplacian over 2m, is equal to En, the function. Let's do it for a second in one dimension. We want something for which the second derivative of the function multiplied by some minus sign and some constant is equal to some En. What are the functions? For instance, in 1D. Well, try this. You take the first derivative and you get down ik. Take the second derivative and you get the square. Multiply by minus h bar square over 2m. I square and the minus just are plus. So you get here h bar square k square over 2m, a number. This number is E. Okay? So we just found that you can classify your solutions by a k, in fact, an infinite, a real wave vector, phi k, and that the corresponding ek is just the expected h bar k square over 2m, like in the first lecture, and phi of k is this. But now comes, is this clear? Okay? So here, for instance, this is a continuous label, not just an integer, as I was mentioning there. And the spectrum, you see, can go from 0 to plus infinity. In fact, there are two values. K and minus k give you exactly the same eigenvalue En. All right? We will discuss this more. But what I want to discuss in 2 minutes, and then we go, is the fact that these wave functions, as opposed to what I was stating here, are not, in principle, normalizable. If you calculate the modulo square, it's just 1. You integrate over an all volume is infinite. Okay? So we have to enlarge a little bit or be less pretentious on our things, and in some sense include objects that can have an infinite normalization in a very special sense, which we will discuss next time. There are a couple of procedures to do this. One is to put everything on a box of a finite volume, L cube, and work with certain boundary conditions that are called periodic boundary condition, and then at the end of the calculation send L to infinity. We will discuss this. People in particle physics prefer much more to work directly with this and rather than requiring the Kronecker delta orthogonality, they require the Dirac delta orthogonality, okay? Which is a way that can be recovered from this, and we will discuss next time. I think that I better stop for the time being here. So this is free particle is the simplest eigenvalue problem that you can study in essentially 3 seconds. And by the way, how do you find this? So if I now give you any initial state, how do you find this way of writing? Well, you have to find a way of writing which is of this form. Integral in dk, the sum now is an integral, times some function c of k times the e to the I kx. Do you remember what we did in the first lecture? We wrote exactly something like this, where g of k appeared there, okay? So the Fourier transform provides exactly a way of calculating this object. So you can calculate for any initial state what is exactly the object that gives you the Fourier transform. Now, what is the evolution at time t? Well, the theory tells you that you can just add here e to the minus ek over h bar t. And you realize that this ek over h bar is just the omega k we introduced last time, okay? So if you go and look at the first, exactly the first exercise we did, which was a Gaussian exercise, and you just remove a little bit of the things, for instance, there is no need for this to be really a Gaussian, can be anything, then you realize that this is indeed of this form, okay, that we stated today. Okay, so next time more about this normalization, and then with more eigenvalue problems in 1D and so on. Questions? Yes.
I have been asked about the difference between photoelectric effect and photon effect.
Yes, I will answer. I don't know if it is. It's not strictly speaking a subject of our course in quantum mechanics. I can tell you the difference now. I mean, I can tell you everybody, but it involves things that are more quantum electrodynamics concepts rather than quantum mechanics. Okay, so I prefer just to avoid the explicit. Okay. So if there are more specific questions, otherwise we reconvene here tomorrow. Okay.